Welcome one and all, Coach Jay here. We are going live right now, literally right now. Hope you're having a fantastic day today. So I just want to, in honor of Michigan today, just share with you my Michigan enshrined wall over there. Gotta love it. Absolutely. Gotta love Michigan. If you don't, then, well, good luck on your test. Hope that works out well for you. No, I'm just messing with you. Hey, I hope you're having a good day today. This is Coach Jay study session. This is chapter 11, right? This is chapter 11, and we're getting started today. Just a heads up today, just kind of giving a heads, kind of a mark where we're at. I'll turn down the music. One of the things that I'm concerned with, I know that I think it was 7th period today I talked with, regarding just making sure that we finish out well before spring break. This is the last official chapter. Y'all get excited. This is the last official chapter. We'll have a little bit of chapter 12 once we get back, but then we're going to start reviewing. So this is imperative that you put the time in because we really don't have very many tests left, really. And so I want to make sure that you finish strong. Make sure your data collection is also put in. Make sure 11.2 is done. And check out this podcast because we are going to help you out as we prepare for this test. So without further ado, we're going to be going left, right, all around. Let's get started. The first thing I want to do is go straight to our test, the ones that we were talking about in class with both periods. It took a little bit of time to kind of look at it here and look at what type of tests there are. Feel free up here. I believe you can kind of Google this. So I think it's at LTCC online. I also put it on the chapter 11 on the top, that link up there. So check it out. But basically what this does is this allows us to see what types of tests they are. And again, what I would mark are these three. These are the three that you'll be tested on come chapter 11. Okay. All right. So let's go through this one. I'm going to go here. States, do people on computers and people on handhelds use the same internet search engines? 1,000 web searches from a computer and 1,500 web searches from a handheld were tracked to see what search engine was used. Well, in this context, we have people on computers and people on handhelds, right? And so do they use the same internet search engines? And so the variable in this case is search engines, with the people on computers and people on handhelds being the two populations. And so what we're going to be doing here is comparing this by doing a test of homogeneity. In this case, what it's happening is we have two populations. And remember, the two populations with one variable means homogeneity. If I have two variables in one population, that's independence, and one variable in one population is chi-square goodness of fit. Let's do a couple more. Do colors of shirts and colors of pants occur at the same frequency? So right now I'm looking and seeing, okay, I've got colors of shirts and pants. 300 people were observed for the primary color of their pants, and 300 were observed for the primary color of their shirt. I think this is homogeneity again. We've got two that are being compared, two different populations, both being compared as the colors that are there. That's being compared with one variable. All right, next one. Do all working hours experience the same productivity levels? Okay. 1,000 employees were observed during each of the 8 hours from 9 to 5. So we've got one population, okay, that's here. 1,000 employees were observed. And do all working hours experience the same productivity levels? Okay. The one variable we're looking at is productivity, right? So I would say goodness of fit. Yeah, so it's one variable, one population, therefore we're goodness of fit, okay? Next one, is the racial distribution the same for UCLA and UCSD? Two populations, 5,000 students from each university were asked about their race. Well, in this case, we should have homogeneity, whatever you say there. We got two populations, one variable. Does a political affiliation of Congress reflect the known political affiliation of the American public? All right, so what I would do here is anytime, if you're struggling on these, pause this and then find the answer out afterwards, or you could even do this online. Does the political affiliate, I think I got this one wrong in class, but let's see if we got it. Does the political affiliation of Congress reflect the known political affiliation? Okay, here's the key. The known political affiliation of American public. So basically, remember, this is our claim, right? We assume this claim to be true, but we're trying to counter it by taking a sample, the political affiliation of Congress, to see does it match up. So I would say that's goodness of fit. Okay. Rockin'. Next one, do colors of shirts, and I think we just did this one, right? Homogeneity. Okay, good. 1974, each acre of the Tahoe Basin was assessed to see what condition the soil was in. Here's the hint. If they give me something like this off the get-go, like with the M&Ms, 30% is this, 20% is this color, 15% is this, it's probably going to be goodness of fit because we're claiming this. And then it says this year the region was assessed again, right? This is the population, the year. And then, again, and the number of each type were again determined. The variable in this case is the condition the soil was in, right? And so we would say this is goodness of fit. Cool. I want to get at independence. Are sometimes at which classes are offered more popular than others. 7 sections of the same math classes were offered and enrollments of each were tabulated. All right, this is where it gets a little bit weird. Are sometimes at which classes are offered more popular than others. So what we're saying is that 7 sections of the same math classes, okay? So the population is the 7 sections of the same math classes, cool? And we're saying they were offered and enrollments of each were tabulated, okay? So basically the variables, the math classes is my population, students in my math classes. The variables are the sections and the enrollment, right? I don't know. Hold up. Which would be more popular? I'm struggling on this one. It's not goodness of fit. It's not homogeneity because we're not comparing anything. We're saying is there an association? Yeah, that's the key, okay? Is there an association between the timing of the math class and the enrollment? I would say that there's an association or an independence. Ooh, and I am incorrect. It says, notice that we are testing for distribution, not for independence. Is it goodness of fit? Yeah, okay. So it says, are sometimes at which classes are offered, and a lot of times the data will help us. If it is not a two-way table, in this instance, we would use goodness of fit. But it says, are sometimes at which classes are offered more popular than others. I guess because we're just simply comparing the enrollment for each course, we're comparing one to the next, to the next, to the next, we'd use goodness of fit. Though I think that that's tricky. I think that there's a possibility, depending on how we do this study, it could be independence. But in this context, I understand what they're saying on that one. That one's a tough one. This one says, is the distribution of ages at a university normally distributed? Counts were taken of students within 1, 2, and 3 standard deviations from the mean. Is the distribution of ages at a university normally distributed? Counts were taken of students within each of these. We would say goodness of fit because if it's a distribution, and again, I don't like this because this could go into other parts of statistics that I feel like would be more other tests that would be better fitted for this, but providing more context would help. But right now we're trying to fit the distribution of ages, right? We're trying to get counts and we're just comparing the counts to that distribution, kind of like that last question, okay? Is soil type related, you could also say associated, to the predominant type of tree that grows in the area? 800 locations with the 10 soil types were observed. Is soil type related, associated to the predominant type of tree? Okay, so here's our population, 800 locations, 10 soil types. And then we look the 800 in the locations is what we observe. That's a population. 10 soil types is one variable, the different soil types, and the type of tree is the other variable. This is independence, hands down. And that's how we would use it there. Hey, I hope that was helpful for you. largely just going through that. I want to make sure that we're all good. We're going to go to part 2 here, mainly because I think this is going to be helpful for you. This next part, what I did was go through just a few question marks of specific things that I felt like would be on the test, things that you need to know. And so what I'm going to do is this. I'm going to, on this slide, first off, I'm going to blow this up just a hair, okay? And by the way, if you do have extra questions on this, this is awesome. Feel free. I already see that there's a lot of people on here. If there's something that you're like, Coach, I'm struggling on, let me know, and I would be more than happy to go through it there. But just I'm happy that you're here. I appreciate the fact that you're putting in a lot of work and effort, and so good work there. All right, so real quick, we have chi-square goodness of fit. Remember, this is one variable and one population. Couple things to note on this. A lot of times we measure sample to a claim. Okay, that's kind of a big thing. If you remember, our activity is M&M sample to what the proposed claim was. Okay, so you might say, well, what's the variable? The color of the M&M was the variable. The population was the M&M sample. Cool. All right, the next one is chi-square homogeneity. Okay, this right here is when we have two populations with one variable. If you remember, this was our two gummy brands, right? But the and so this was our population, and then we had one variable, which was our color. We compared our color. A lot of times we say words that would be described by this is comparing, right? If we say compare, if we say, a lot of times we say, we have to assume that the two populations are in fact equal, that the population distributions of both the gummy bear types, that they are, they have equal distributions, right? And then the alternative would be that they're not the same, that the distributions are not the same. And we'll look at that a little bit later, but a lot of times they're comparing two populations within one variable. And last but not least, we have our chi-squared association or chi-square independence. In this, we're looking to see, does one affect the other, right? A lot of times in this case, we have two variables with one population. A lot of times they actually use the word association, which gives it away, right? Sometimes they'll use the word, I'm trying to think, like this one was one, males, does gender, male or female, affect subject content, okay? So these were the two variables. And we sampled a group of seniors, right? So we sampled one population, and we were trying to say, or see, did gender impact their the favorite subject that the individuals selected? So in that instance, the variables would be gender and the variables would be subject. Notice that chi-squared as well as chi-square homogeneity have the same type of steps. The only difference is the hypothesis and the conclusion, again, which we'll look at here shortly. Okay. Conditions that need to be met. Couple things. Make sure you put random. Make sure you put what the random is. 113 randomly selected, right? You could put that. Make sure you do put that down. The second thing is 10% condition, which is our independence. Remember, if there's one population, you could put the total. But if you have two populations, such as the Haribo and Walmart brand that we did in the gummies, you would put your total here. So let's say we sampled 77. We would say 77 is less than or equal to 1/10 of all Haribo gummies, right? Which is true. We just want to show it. And that's check, check. Let's say we selected 100, and maybe in the Walmart brand, we just say all WM or Walmart gummies. And that's what we'd put there. Okay, that's our 10% condition. So we've got random, we've got 10%, and then we got large counts. All right, with large counts, we are going to say that all expected values are greater than or equal to 5. And you could also, I've seen this put that the least number, just put it in context. As long as that's greater than or equal to 5, least number expected value. If that's greater than or equal to 5, that's sufficient as well, okay? You could put any of those for your conditions here. Your chi-square summation formula, remember that, again, you can use your formula sheet. I find that if I know them going in, or at least know the overall, like just the overall basis of them, I know where to kind of go on my formula sheet. It saves me time. So this would be the formula for summation. This is our chi-squared, which is our test statistic. Okay, test statistic. Remember the graph of this would be always skewed to the right. The value that we start at is our chi-square value, and the area that's highlighted is our p-value. Notice since this is squared, we always are going to have a positive value. So this always will start with 0 and go from there. I will also recommend that when doing this, that with the chi-squared, we have to at least show that 1 observed minus expected squared divided by expected plus ... And I would just put 2 of these here, okay? I'm sorry, minus expected squared divided by expected. And just tell me that that's equal to chi-squared, okay? We're going to look at our calculator here in a second to help us out with this. It's always positive. We already kind of hit on that because we're squaring a value. Anytime we square a value, we're just seeing the distance that's away from it. And that allows me to see what the test statistic, how far is my expected and observed, how far are they away from each other. Remember degrees of freedom. When we talk about chi-squared GOF, it's always categories -1. Sorry, -1. That's huge there. And within our chi-squared homogeneity or independence for both of these, the degrees of freedom, which is very important, is going to be column -1 times row -1, and we multiply that together to get what our degrees of freedom is there, okay? Trying to think. Oh, yeah. If I found my expected value on a chart, just as a heads up here, I want to see if I can find one. Yeah, this is good. We'll blow this one up just for a second. If I was finding the expected value of, let's say this right here, these are all the observed. What they give you is the observed. To find what the expected is, I go to my row column. I'm sorry, row total times my times, not added. Some people were messing that up a little bit today. Times my column total. This is not on your formula sheet, just a heads up. Divided by my table total. Okay, so if I go 539 times 234 divided by 687, you could get what your expected value is. Okay. Another thing to kind of I would recommend as well is if you forget that, you can always go into your calculator to plug it in and hopefully get it out, which I'm going to hopefully show an easier way to get that done here shortly. Okay. All right. Let me see if I've got anything here. I don't have anything yet. That's cool. Null hypothesis for chi-square tests. We're going to look at that because that's going to depend on what test we're using, and we're going to go on the next slide and hit that, okay? The only other thing that I would say is if I said chi-squared is 10.21, and I say, based upon this, do we have convincing evidence to reject the null hypothesis, okay? What this means is this test statistic is 10.21. To find my p-value, which allows me to reject or fail to reject the null hypothesis, we then go to chi-squared CDF on my test and go lower bound, which would be 10.21, comma upper bound, which is a large number, comma degrees of freedom. And that depends on the context there, but that's what I would do on that one, okay? The calculator we're going to hit on, normal CDF to probability, okay? The only other thing I would say here, and if you're watching this right now, then good on you. Really good on you. Let's say that we have 100, okay? And this is the mean, okay? So let's say it is a normal distribution, the mean being 100, and the standard deviation is 10, okay? And the question becomes, what is the probability of selecting, and by the way, this is on the test, this is just a heads up, a value between, let's say 70 to 90, okay? So we're talking about a test, let's say. This represents our I don't know, let's say the test is out of 200, okay? This represents that test. So the probability of selecting a value between 70 and 90, we can go, if we say it's already normally distributed, we can say that the 90 value would be about right here with the 70 here, right? So what I'm trying to do is find what is the probability of selecting this, which is in essence similar to our p-value, right? We're trying to find the area underneath this curve. If the whole area is 1, the probability of selecting this would be definitely less than 1, and it would be a sliver of this. So to do that, we could go normal CDF, my lower bound, 70. My upper bound is 90. My mean is 100. And my standard deviation is 10. Cool. And that will allow me to get to where I need to be for that part of the test. Cool. All right. All right. So with that being said, I am going to literally, I'm going to fly through this. Okay. So we did that in like record time. I'm going to really spend a lot of time here. I will tell you that all of the multiple choice, which we can go through a couple here, but all these multiple choice are online underneath the Google form. It's on the right side, top right side of the on-campus page. So feel free to go through those if you need to for some extra practice. But the number one thing that I kept hearing was, Coach, could you go over the difference between the 3 different types of FRQs? How do we attack each of these? And how they compare. So first off, let's do this. We are going to literally take the 4-step process. Cool. And we're going to do this on, show you how to do it on a calculator for all 3. And so we're really going to hone in right here, okay? So first thing is we've got to identify what test is going on, okay? One thing that I would recommend too is maybe towards the top putting 2 things that might help you out. First of all, a graph, a picture of some kind. That always helps me. It's again skewed right. We remember that this is the chi-squared test statistic, and this right here is our p-value, right? So all of these are, again, 0 or anything greater than 0. So you could kind of put in, for all 3 of these, the same exact picture. The only thing I would make sure of is this is the chi-squared, and when you find chi-squared, actually plug it in. And then this is the p-value where we start at 0. Cool? I want to make sure I put this in for each. Okay, so the state part. Let's talk about what type of test we have. First of all, and that's important, I would identify that as early as possible. It says this: shopping at secondhand stores is becoming more popular and has even attracted the attention of business schools. A study of customers' attitudes, okay? Customers' attitudes towards secondhand stores interviewed separate, okay, this is huge. If I interview separate random samples of shoppers at how many? 2 secondhand stores. So right now, if I have 2 random samples, that means I'm taking from 2 populations. That's very, very important, okay? Of the same chain in different cities. The two-way table shows the breakdown of respondents of store A, population B, and based on the male and female at store A and store B, okay? So we've got one variable. In this case, we're talking about gender, okay? So when we have 2 populations and 1 variable, that only can mean one thing. We are comparing 2 populations. Think the gummy bears, right? 2 gummy bears, comparing them, comparing the colors. So in this instance, we're using a chi-squared homogeneity. I usually put homo-G. Got me, homogeneity. It's fine. Genety or something like that. So the null hypothesis, if I'm comparing 2 populations together, okay, we are saying that the distributions are the same. That is always, always, always the case. You need to understand that. Big, big part. So on this, we would say the distribution of, and I'm doing shorthand, but I would really recommend writing it out. The distribution of the populations concerning gender, the distribution of the populations concerning genders who shop at the store is the same. Cool? All right, so that's the first thing. The alternative, let's put the alternative here. And I hope that this makes sense. I'm just going to do the same thing. The distributions of the populations are what? Different. So what we're trying to show is that, in fact, they are different. But in order to show that they're different, we have to assume that they, in fact, are the same. Okay? So coming back up here to the next one, we're going to do number 3 here. Okay, so we're going to do this one in blue. The null hypothesis states that casinos are required to verify that their games operate as advertised. That's key. Operate as advertised. American roulette wheels have 38 slots, which mean 18 red, 18 black, and 2 green. In one casino, managers record data from one random sample, there's your one population, of one of their American roulette wheels. The table displays the results. So this right here would be obviously the totals, right? But as we look at this, we're looking at just color. So colors are variable, one random sample, 1 and 1. We're comparing our sample to our expected values, which we'll look at. We haven't really converted them to expected values, but you get the idea. So in this case, what we would do is one variable to one population. We would then say that the sample distribution oh, wait, hold up. I can kind of make this a little bit. We actually have to assume that the claim that they are saying is in fact true. Okay? So the claim of the one casino, the claim of the casino having their game operate as advertised is true. And then the alternative, guess what we would say? The alternative that we're trying to show is that the claim is in fact not true. Okay? All right, so this would be the null and the alternative. By the way, I have not put this down. One thing we can also put down here for all of these is that our sig level is 0.05. It's assumed that. I haven't seen anything that has been different, but that's not to say that there won't be. But traditionally, it's at a 0.05 level. The next one, General Social Survey asked a random sample of adults. That's key. Their opinion about whether astrology is very scientific, sort of scientific, or not at all scientific. Here's a two-way table of counts for people in the sample who had, here's the next one, 3 levels of higher education. So their response is here. Cool. This is their response, but their 3 levels of higher education would be variable 2. These are the same people. So this is still one population, but we're using 2 variables to see if their opinion is because it has an association to what the degree that they hold. So what we would say is, for our null, again, we have the picture, make sure of. And by the way, this would be chi-square up here, chi-square GOF. I don't know if I put that there. And this is chi-square independence. Okay? So we would say that there is no association. We always have to say no association between one's opinion trying to see random sample of adults. So we're good. One's opinion on astrology compared to the degree they hold. Okay. And I'm not 100% sure on this. If you state context here, I would probably, I mean, I guess you could put this too. But then I would say the alternative is there is an association. And between one's opinion on astrology compared to the degree they hold, okay? But you would put context here. So the state would be all of those things here, okay? Now, here's the kicker on this. The next one in the plan phase, okay, I'm going to put P for all of these, okay? We already put all the tests there. So if you didn't put the test, make sure you put it in the plan phase, which is where we normally would probably put that there. Make sure we put random, which it states in the problem, and make sure you state something about that, right? So like, for instance, this random sample of 200. Make sure you say each of these, okay? The next one is independent. Well, really 10% condition. Just show 10%. 10%. I do want to hit on this because this is important. Remember that if I have one population, like these two are one population, you only have to show this once. So if I had 200 spins, I would say 200 is less than or equal to 1/10 of all casino spins because there's only one population. Down below, even though it's a two-way table, this has a simple random sample of adults right here that were selected. Well, let me make sure. Boom, boom, boom. Yeah, in total, there were 687 people, right? So the 10% condition, even though there's a two-way table, you would say 687 less than or equal to 1/10 of all adults, right? Because that's the context of what we're looking at, right? Sample of adults. For this one up here, because there are two populations, store A and store B, right? Let me give you a hint here. Separate random samples, that's key. That allows us to see that we'd actually have to show one for part A and one for part B because we have two populations. Cool? So just be sure of that. And then our final thing is a little tough because we don't really have the large counts here. But in large counts, you could put one of two things. You could say all expected values are greater than or equal to 5. Since if you do put the expected values, which I would recommend the chart or something just to help you out there, I could just say the least expected value is greater than or equal to 5, and then actually list it here. Like, what is the least expected value, right? The same thing goes here. So least expected value is greater than or equal to 5. And then actually list what that is. And the same thing goes for this one down here, okay? So all three of those are the exact same with what we're looking at on that one, okay? Cool beans, cool beans. I hope this is, I want to make sure I do just a quick test. So we're all good here. Good, okay. Just want to make sure that it's still rolling. Okay, so as we go to the do phase, this is where it becomes tricky, okay? Within all of these, okay, every single one of them, picture, we've already stated that. We've already got that there, okay? All of them will have observed minus expected squared, right, over expected. Each of them will have two of these shown, right? Observed minus expected squared over expected plus ... Observed minus expected squared over expected, and this equals my chi-squared. So all of these, when I put these lines, that just means that these first two things, numbers 1 and number 2, are going to be the exact same. Now, how we find the expected, I'm going to show you that here in a second. But I do want to make sure that you know that numbers 1 and 2 are the exact same. Now, how we find chi-squared and how we find our p-value is a little bit different, okay? And this is where we're going to show, this is what we're really going to make sure we do to make sure we understand what we're doing here. So I'm going to do these two on my calculator here in just a second. But before I do, because this is just a single chart, just kind of chart laid out, in total there are n equals 200, right? All right, so if there are 200, what I can do on this to find what the expected value is I can first find what the probability out of the 38 slots, and I would actually make like an expected, I would actually make an expected chart for all these, okay? 1, 2, and 3. Maybe even do that in the state part, just so you've got it listed. But you've got your color. So this is the observed. My expected values would be color here. You got red, black, and green. Cool. our counts, our expected counts. This is, I'm trying to see the proportion. So this is 18 over 38. I'll do that. 18 divided by 38 is 0.47 right there, 0.47. If I took 0.47 and multiplied it by 200, right, you would expect out of 200 to get 94 here and 94 here, which then if I only have 2 green and I put 2 divided by 38, okay, I'll show you this, divided by 38. It'd be about 10 and a half. And so I would say, about, let's say 11, but this is 188. So we could just say, give or take about 12. I would make sure that I had a decimal here, but to find these values, remember it's the probability of whatever x is. So the probability out of 38, we got to convert these two percentages. This percentage was, well, let's do this one first. This was like 10.5%, right? Or actually, let me make sure of that. 0.05%, my fault. The expected was 10.5. So 0.05%. And these two, 18 out of 38, had a probability of 47.4%, okay? So these are the percentage. To find the actual expected values, we do the probability times my total of n. So 200 times 47.4 is approximately 94. We do that for red, black, and green. Cool. And so this right here would be our expected values right here and here. Okay. Now this one becomes much easier because to find it on our actual calculator makes it simple. So let's go and do this one first, but we're going to do strictly every one of these off of the calculator and hopefully be able to show you the difference between the two, and then we're going to conclude, and then we'll be Gucci. Okay. Be Gucci here. All right, let's go. So for this one, with the goodness of fit, we can go to stat. And again, we live in test world, stat test. And we go to chi-squared goodness of fit test, which allows us to put in the observed and the expected. Now, before we do that, though, we've got to actually put in what is L1 and L2. So we go to stat. We go simply to edit. Again, we can always delete and just come downward if that helps us here. Ooh. I think I messed that up. Did I just mess that up? Did I just delete that? Should have said cleared and then gone. I think I did delete. Let me do this. Let me go second, memory, reset this. Because it might help me also on some of this other stuff. So coming back to stat, let's go to calculate. I've hit the wrong one. If that's you, it's okay. You can just kind of start over. Or you could just replace it. That's fine. So my L1 list would be my totals here. So my totals that I'm finding are, I'm going to pull this up. And again, this is on the first one here. Okay. All right. So make sure I've got my calculator up. Okay, perfect. So my first one that I would plug in for this would be 85. 99 and 16. Cool. The second one would be 94, 94 and 12. Okay. So the observed would be L1. The expected would be L2. So we're going to go to stat. And in the test, we go to our goodness of fit. The only thing that we need is the categories. Well, we have 3 categories. So remember with this, we do 3 minus 1, which would get degrees of freedom of 2 in this context. So we can calculate it to give me a test statistic of 2.46 and a p-value of 0.29. 2.46 and 0.249. Okay. So this will roll right straight into my conclusion, which remember from our null hypothesis, if you're doing it on this, the null hypothesis said that, in fact, the claim was true, right? The claim that they're saying was true. And our alternative is if we can have significant evidence to reject it, if our p-value is less than 0.05, we have convincing evidence to reject it, to say that, in fact, this American Russian wheel is not operating as advertised, right? So we would say in this case, because, and I'll do very like what I'm expecting, right? So because P is equal to 0.249 and it is greater than our alpha level of 0.05, we do not have convincing evidence to reject the null hypothesis, okay? And then put a little context in there, which means, what does that mean? Which means we do not, or I would say, which means we state I actually flow with this. Usually I put a little context at the end. We do not have convincing evidence to reject the null hypothesis, stating the claim of, and I would even put, and just make sure it's true. I probably put something in here that stating that the claim of the fact that the Russian or the roulette wheel operated appropriately is true. Okay. All right. Does that make sense? I hope that makes sense here. Now let's go to this second one. We're back to number one. Remember on this one, we're going to plug in these values right here in for our calculator. So a little bit different here. And I think I am actually doing this without you seeing it. I'm sorry about that. Let me come back here. Actually, let me do this. Let me stay on the calculator, and I'll come back, and you'll be able to see it after this test, okay? All right, so the next test we're going to do is we're going to go and do it in a two-way table, second x to the negative first. Holla to Max out there, Miss Wilson, for helping us out with this. In this, we're going to go to edit on this, and we only need to put the observed. Well, since this is a 2x2, that's here. We've only got we got a male and a female and two stores. We have 2 by 2. And we're simply going to put just the observed values in. So we're going to put 38 in, 68, 203, 203. And make sure you do plug those values in. That's important. And 150, okay, so we plug that in. You do not have to put the expected values in. This is great. This is a new addition here. Some of you in my 5th period did not see this yet, but we actually do not have to plug it in, only for matrix A, which is our observed. Now, we could find this, right? We talked about earlier in the podcast how we do it by hand, just in case. But let's say that in this instance, we wanted to do it by calculator. We could go to stat test. We go to our chi-squared test here, because it's not goodness of fit. The expected, though it says B in there, this actual expected value will, you don't have to plug the expected in. It will do that for you. So when we go to calculate, it'll shoot it out at us where our chi-squared value is 15.33. Our degrees of freedom was 1. And our p-value was 9.007 times e. Make sure you don't miss this here, right? We can't have a p-value that's 9. It's got to be less than 1. So make sure if you see that e to the negative 5th that you know that that's scientific notation, which is a small, small, small number, okay? Now, if you did want to get your expected value, you could go to second x to the negative first. And actually, I would quit out of all this and go to second x to the negative first. And notice I didn't plug anything in for b. And you don't have to delete it each time. You do not have to delete it. So once I get here, I can just simply come to B, press enter again, and there are my expected values for this problem here. Okay, so I got to find what my expected values were, and you could always plug those down if you want to, or if you need that on a FRQ or multiple choice, you have it. Just make sure in this area that you definitely show your work there. That's going to be important, especially for the problems that you got to kind of know both sides of multiple choice, right? So remember, If I did it by hand and I found the expected of the 38, I do 106 times the row total times the column total of 241 divided by 459, which is my table total, to find the expected value here. Okay. But in conclusion, I think we have, make sure I pull this back up. Anyway, I think it was, and this could be off a little bit because you were writing it down, but 15.3 something, I think. And this was like 0.0239, right? Which is a small p-value, right? And by the way, this was our conclusion for that one I did previously. But the conclusion here would be as follows. I would say we do. Let me start with my cookie cutter response. So because P is equal to 0.0009 and it is less than our alpha level of 0.05, we do have convincing evidence to reject the null. And then you could just say which states, which means, and then this is where if I reject the null hypothesis, then that means that we can, which means we accept the alternative. We accept, and what was the alternative up here? The alternative was that the two stores are different, right? The two stores have a different, because this is a chi-square test of homogeneity here, that these two stores have different distributions compared to gender, which means we accept the alternative stating the two stores distribution of gender is not the same. Cool? And that's how we would list that there. Okay? So again, this is chi-squared of homogeneity. Okay? Because of two populations. Now with this one, we're doing association. So let's do this one more time. We're going to do it. This time it's a 2 rows, 3 columns. So a little bit different here. But we'll wrap it up with this one here on this side. I hope. I know you're probably thinking, Coach, what? I thought we were going to go through a lot of multiple choice. And we will. Tomorrow, we're going to spend some time as well kind of going over some of that in class beforehand. But I do want to make sure a lot of the multiple choice are actually off that. So if you need some more multiple choice, I would say practice it. And then if you have questions, come on in and we'll look at those later on, okay? So we're going to do this again. So second x to the negative first. We're going to go to edit. We're going to go to A. This time it's a 3 by 2. And I'm going, 2 by 3. Make sure it matches your table if you're confused. So 2 rows, 3 columns is what we're looking for. All righty. We've got our 169, 256, 114, 65, 65, 18. And there you are. So then we can go to second mode and get out of there, right? Because we put it in. Then we go to stat, go to test. Remember, I did not put in B. Same thing. Observed is in there. Expected, we don't have to change B. We just simply push calculate. And there we are. Our chi-squared is 10.58. Okay. We got 10.58. And our p-value is 0.005. Cool. And I'm just put that down. Our degrees of freedom is also 2. The reason why the degrees of freedom is 2, because we have 3 columns, we do 3 minus 1 is 2, and we multiply it by the row total minus 1. So that'd be 2 minus 1, which would be 1. So in total, we have a degrees of freedom of 2, which actually gives it to us right here. But it's important to know that for the test on there, okay? All right, again, just as a heads up, you can go to second, x to the negative first, go simply down to B, click on that, and that will give you what the expected values are. And you could just go to the right side here to kind of get the far right side here as well. Remember, too, do not put in your totals, only the the variables or population of the two-way table is what we're expecting. Cool. All right. So in conclusion, I'm going to go through this quick. I'm hoping but it doesn't take too much time. I know it did take a while. But in conclusion, we do have convincing evidence. I would do the same thing, right? Because P is equal to 0.005, it's less than 0.05. We do have convincing evidence to reject the null hypothesis. Here's the kicker. Go back to your null hypothesis that we stated and the alternative. If we reject the null, okay, which means that we can reject our null, and we can accept the alternative, and the alternative is that there is, in fact, an association between the degree someone holds and their opinion about astrology. Got me? So there is a association that's there. Remember, our null hypothesis is that there is no association, always with context. And then if we have a convincing evidence to reject, we would have state that we do have convincing evidence to reject the null hypothesis, stating that the alternative is true, which was in context the fact that there was an association between the degree one holds and the opinion about astrology. Cool. All right. Man, that was a lot. Here's the deal. As you go through, these are really, really important. We hit on a lot of these already. In fact, as I go through, feel free to pause this video as I slowly go through some of these multiple choice questions. The answers are at the bottom of chapter 11 if you're looking for those. If you need some help on these tomorrow, I would be more than willing to help you out with those. In fact, we're going to have multiple people that are going to be helping out tomorrow. And I'm excited about that because that means we're going to have a ton of teachers coming around trying to make sure that you're ready to go and squared away in the first 30 minutes. So make sure of that. I'm excited about it. Make sure, again, chi-squared CDF, this is a good one. Number 9, just a heads up, it says it gives a test statistic of 69.8, right? So here it is. This test statistic is 69.8, and the p-value is close to, so p is approximately 0.00, right? The correct interpretation would mean that since this is, in fact, and by the way, I could find that by doing the chi-squared CDF of my lower bound to my upper bound, 69.8 to my upper bound. We don't know what the degrees of freedom is because it doesn't give it to us, but we then put that at the end to find it there, okay? So just a heads up on that as we go through, as we go through that there, okay? Here's again numbers 10 and 11. You can pause there. Number 12 and then number 13. Cool. Just again, something I want to make sure that you have that there. And really, I hope that this was helpful for you. My whole thing is that going through this, hope that you were better, you feel better. I feel good about this test. For those that prepared, I feel like the material, we can dominate this. But the big thing is knowing those multiple choice questions, how it's applied, and making sure you're prepared that way. Hey, I appreciate y'all. Thank you so much for showing up. And have a great day. See y'all.